I'm going to run through it now in full, record the video, and then upload it so you can take a look at it. I sent an email that the homework is still going to go live tonight, but I've extended the deadline from Monday of next week to Friday of next week, so hopefully you should have plenty of time. Unfortunately, I can't figure out how to get the video of myself in like the corner. I don't think it's super important since you can't really see like what I'm pointing to, but hopefully it's not too distracting. I also can't take any questions, obviously, since I'm recording it, and I can't see if it looks like you're understanding. So if anything is confusing, definitely shoot me an email at any point when you're reviewing it or post in the discussion board on Blackboard. Because I'm sure if you don't understand it, someone else doesn't as well, and I can try to clear up any confusion. Okay, so let's get started. So the outline for this lecture is going to be at a high level, unsupervised learning. Now, so far throughout the semester, we've kind of covered supervised learning topics, and we've thought about this through the lens of like similarity, right? I talked about this already in those like first 15 minutes I was able to capture, but like basically overall, like all the models we've been trying to build and all the things we've been trying to do have been trying to find things that are similar, right? Like find people that are similar. Basically figure out how far apart are things. And one more way to kind of formalize this, or one more thing we can kind of get out of this, is we're going to cover one last supervised model, and we're going to use that to kind of build us up to this unsupervised learning, which is like the overall kind of topic for today. And then we'll talk about some unsupervised models. And then I'll kind of cover some interesting, I think, demos of unsupervised models. The last one here, recommender systems, is one that you're probably kind of familiar with. It's one I've talked about throughout the semester. It's the idea that, like, can Netflix basically recommend what movies you might be interested in, or can Amazon recommend what products you might be interested in? And we'll kind of look at some examples of this. Okay, so to get started, I just kind of want to formalize this idea of similarity, talk about how we've used it already, and then how we are going to use it to kind of work on the unsupervised part of today's class. So the first thing we probably want to answer is, well, why do we even care about similarity? And I think this whole topic of similarity is kind of intuitive. Some of the math behind it might not be super like clear as to why we're doing it, but I think overall the high level idea of similarity should kind of click and hopefully be useful and understandable. So the idea is that if two items, like two people, are similar in some way, they are probably similar in other ways as well, right? If two people have very similar medical histories and medical like diagnoses and kind of like medical test results, they might suffer from similar illnesses, right? They might be equally as likely or similarly as likely to get admitted to the hospital or to have to extend their stay in the hospital. People that have the same or similar ages and genders and incomes and occupations might treat credit cards in a similar way, right? This is obviously not always true. People who have those similarities might treat credit cards in totally different ways, right? But the idea being that, like, if they're similar in one way, it's definitely possible that they're similar in others. And in supervised learning, we're going to use, or we have used, similarity for classification and regression. We've used similarity to kind of like build branches in decision trees, right? Where we were trying to find people who are similar to one another to build that branch. And we'll see an example of this that we've already covered, but we'll look at another example again, just to really bring that point home. And in unsupervised learning, we are not trying to predict any one thing. We're just trying to find groups of similar items and put them together into what we're going to call clusters. This isn't super obvious, like what this is trying to do, or it might not be super obvious how this is different from supervised learning in this like short little description here. But as a reminder, they are different in that supervised learning is trying to predict a single target variable, whereas unsupervised learning is just really looking at the similarity-ishness, trying to find trends, but not predict any one thing, right? And when we look at examples and start building these models, the unsupervised models, you'll see. So just to kind of like at a high level talk about different applications that might use similarity, right? Again, I mentioned in that kind of outline for this lecture, but recommendations heavily rely on this, right? One way to do this would be to find items that are similar to items that you've already expressed interest in, right? And this might be the form of like Netflix movies, where you like one movie and then Netflix recommends movies that are similar to that one. Like maybe you like a superhero movie and it starts to recommend other superhero movies because those movies are similar to one another. Another way to do this to build a recommendation would be to think about similarity, but from the person who's experiencing it, right? So like I might watch a superhero movie and instead of Netflix recommending other superhero movies because they are similar to that one, it might look at my friends, right? And the movies that my friends like, assuming that my friends and I are similar because we're friends. And then it might just look at what they're interested in and start recommending me new things. And this is interesting because it helps you like leverage the complexity of people, right? And leverage those similarities. Superhero movies is probably like a very niche kind of small category, but I'm sure I have friends who are interested in other things that I'm just not aware of, right? And it's like one way to kind of like help bring that connection about. So just two different ways of thinking about similarity, but I think very important. Another application of similarity would be something like an image classification, right? Where we have pictures of dogs, say, and the dog pictures might be similar in some way. They might have, these like four kind of longish things, right? And those might be like legs, or it might have something to do with ears or a nose, right? Or something about like fur on a dog or a tail. Right? And these kind of have things in common. They are similar in some way. It's a little harder to quantify the image part, but we could talk about that in the future. But like image classification is really just trying to find similarity. Okay, so earlier this semester we talked about similarity, and we used it to help us build something like a decision tree, right? And I think this is like a very clear example of how we view similarity, right? This is basically saying, hey, take some people, right? Take our records, which are people in this case, and take all the people who have a balance of less than $50,000 and who are less than 50 years old, right? And these people are similar, right? In some way, they have similar balances and ages. And we're trying to say that those similarities in balance and ages are also, tend to lead to similar write-off probabilities for a loan, right? Just like people who have a balance of over $50,000 and are over 45 years old might have similar write-off outcomes, right? So this is literally just showing you similarity. It's trying to build groups of similar people, right? And use that to predict something. In this case, if we're going to write off their loan. So to like kind of quantify this idea of similarity, we're going to obviously bring in some data. And just as a reminder, this was on your midterm, so hopefully this is a very easy refresher, right? But we can represent people or records as feature vectors. So I might represent John here. He might have an age, an income, and a number of credit cards, and I can build a feature vector for John, right? Where the vector here is just three numbers. It's his age, his income, and his number of credit cards. The same for Kim or Rachel, which I messed up, but right, she is just represented by her feature vector. I have three features, and my feature vector is three things. So to think about similarity, we're going to think about distances. The idea being that things that are more similar to one another are closer together. This might seem kind of silly at first because you think of distance as measuring, something like miles or feet or meters. But we can think about distance in many different kind of measurement units, right? It doesn't necessarily have to be like physical distance. The first two distances here you use every day, whether or not you do. These are two names that they go by. When I quantify them and show what they actually mean, hopefully you'll realize how you use them every day. The other three are a little more niche and you might not be familiar with them, but we'll still cover them. So Euclidean distance, I feel like I've already mentioned this like 30 times tonight, but Euclidean distance is the shortest distance between 2 points. So for example, if I had point A and B on a map, maybe A is my home and B is my office, right? The shortest distance to get there, to get from my home to my office, would be a straight line, right? If I was taking a helicopter to work, that's exactly how I would probably go. I would get into the helicopter, it would just cut straight across, do the shortest possible path, and it would get there, right? To actually calculate this, you would do this kind of square root distance calculation I have at the bottom of the slide here. And it might look a little confusing, but all it's really doing is saying, what is the difference in the x values of these 2 points and then the y values of these 2 points? And you just kind of plug them into this equation. This really just reduces down to like the Pythagorean theorem, which you covered in like middle school, right? A squared plus b squared equals c squared, where we can think of like this is edge A, this is edge B, and then this is edge C, right? And that's just kind of like what this calculates out to be. In this case, I'm only covering a case that has 2 kind of values, right? X and Y. Each point, we can think of them as records. Each point or each record is only represented by 2 values, X and Y. But, a feature vector can be more than 2 things. It could be, in this case, 3, right? Age, income, and credit cards. So here that would just be like, instead of X and Y, we might have age, income, and then another one, a third kind of value as the number of credit cards, right? And the reason I don't show it here is because I can't really show the 3D space as easily on a 2D slide. But the calculation would be similar, right? You would have like age for person B minus the age of person A squared plus the income of person B minus the income of person A squared plus the number of credit cards for person B minus the number of credit cards for person A squared, and then square root that whole thing. And this would work for 3 or 4 or 5 or 6 or 1,000 features. Manhattan distance is similar in that it's still trying to find this distance between A and B, and it's also similar in that you use this kind of in your everyday life. This would be the more practical way for me to get from my home to my office, right, from A to B. And this just has to basically only travel along routes that are made up of paths that are perpendicular to my axes, right? So if I had X and Y here, where X is the horizontal and Y is the vertical, I can only travel horizontally or vertically, right? Horizontally or vertically. This kind of looks like a stair shape, but you can see that it would be equivalent if I went all the horizontal and then all the vertical, right? And it's called the Manhattan distance just because this is what it kind of looks like to move around and the distance between things in a city. No one really tells you that the distance between 2 points in like meters or miles is straight through buildings, right? They would tell you like kind of how many blocks and how many avenues you had to go. And it's similar here in that, I can't really point to it when this thing pops up, but it's similar here in that if I wanted to find the distance, the Manhattan distance between points A and B, I would take the difference in their X values plus the difference in their Y values, where I'm taking the absolute value of each of these each time, right? And the reason I'm doing that is because XB minus XA kind of gives you all of this X value between X and A, or B and A, I'm sorry. And the same for Y, right? It gives you the distance between B and A and all their Y. And if you add those together, you get this full path. And again, this works for 3 points, or for 3 like 3D examples, right? Where instead of just having X and Y, I have X, Y, and Z, or I have age, income, number of credit cards, right? And that would just be tacking on plus another one. And this yellow dotted line would be the Euclidean distance, right? So you can see how they're kind of related. Jacquard distance is a way of measuring the similarity between 2 sets, right? So if I had sets A and B, which we might think of as like a basket of things you're buying in a supermarket, right? Like say you're person A and you are buying an apple, strawberries, lemon, banana, grapes, and I don't know what that is, plum. And person B is buying lemon, wedges, an apple, strawberries, on and on, right? So if these are 2 different sets A and B, we can calculate their distance as this metric down here. This Jacquard distance of A and B would be equal to 1 minus the size of their intersection divided by the size of their union. Okay, and you can, like these 2 pictures here kind of demonstrate what an intersection and a union is. So the intersection, this little upside down U, is basically if you had set A and set B, what items do they have in common, right? And you can see up here that both people are buying apples, they're both buying strawberries, and they're both buying lemons. The union is if I was to take both carts and kind of add them together, but remove duplicates, right? And that's the key here. So you'll see here that like I'm just kind of taking everything in both baskets and putting it together. And you'll see that I had to get rid of these 2 grapes here, and I got rid of this cherry, and I got rid of the fact that they had, they both had apples and they both had strawberries. I just take one of each thing, get rid of all duplicates, and then I get what the union is. And these little bars here just mean how many things. So this would be 3 for the intersection, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things for the union. Another type of distance that you might not be super familiar with is cosine distance, and this is just the angle between 2 feature vectors. So before we saw feature vectors for John and Rachel, but here we might have record A, B, and C, or person A, B, and C, and they're only defined by 2 features, again, so we can easily plot it. And the cosine distance is a little weird to visualize, but it's essentially the angle between 2 feature vectors. If you were to like draw them out, the vectors in physical space is like, what is that angle between them? And this is calculated as 1 minus, and then the dot product between A and B divided by the size of A times the size of B, right? And this would give you the kind of the angle between 2 things. And it has some benefits. It's mostly used in text classification problems because it ignores the differences in scales between different records. But you often really only see it in text classification problems. If you're not familiar with the dot product, it's a quick Google refresher, but it's essentially just a little bit of multiplication and addition, so not super crazy. And these 2 things here are magnitudes, so like how many things are in A, how many things are in B. So the dot product here would just be A1 times B1 plus A2 times B2. So that would be like 7 times 2 plus 3 times 3 for A and B here, right? This would be A1, this would be A2, and then B1, B2. And then this is, it's called the magnitude, or the norm. And it's basically, it's not the size of things, because there's 2 bars here. So the norm would just be, for A, would be 7 squared plus 2 squared, and then the square root of that. So an easy calculation, similar for B. And then you just multiply them together. Okay, so the last distance measure we're going to talk about is edit distance. And this is another way that people kind of do like spell correction. This is there's a map example here. This is often how it is done in like something like Google Maps. It will basically try to see how many changes I need to make to make one string look like another. It's kind of weird to think about it as distance, but it is just another distance metric. So for these 2 things, right, to make them the same, right, I would have to remove a 1 from the second example and then replace an E with an A, right? And you're only allowed to do these operations. You can only insert, delete, and replace characters. So I deleted 1 and I replaced 1, right? So it has an edit distance of 2. There were 2 changes that had to be made. So what is an example of using this, right? So one of my favorite examples is whiskey analytics. So given a scotch that I already know I like, can I find similar ones, right? And this should be something that everyone can kind of understand. Maybe you don't like scotch, but it could be through food, or it could be a different type of drink or a book or something, right? I like one thing, I want to find things that are kind of similar to it. So if I had a data set of different tasting notes from scotches, I could consider scotches to be feature vectors, right? Just the result of like their tasting notes. right? And let's say that I'm measuring a few different things here, like the color, the nose, like how does it smell, the body of the scotch, what it does to your palate, like is it dry or fruity, and the type of finish that it has when you're done drinking it. Right, and these are just features that I have. So let's try to find the most similar scotches to the Scotch Bunnahabhain, right? And these are the features that Bunnahabhain has. It has a gold color. It's fresh and has like a salty kind of sea-like smell to it. It's a firm body and firm, medium, and light. And it's got like a fruity, sweet kind of palate and a full finish. Right, so here's my whiskey. Here are my descriptions of it. And I'm taking the Euclidean distance, right? So I have a whole bunch of features. And I take the Euclidean distance between a whole bunch of other scotches. And these are the ones that are closest. The actual list of scotches is very, very long. But I'm just going to take the like top 5 here. And you'll notice some of them are actually identical, like these here. So the idea being that if I like Bunnahabhain, at least according to tasting notes, I might find, don't know how to say this one, but I might find that this Glenglassaugh is the most similar to it, right? Or I can go a little further on and try some of these other ones. So predictive modeling so far. So tree models, right, have kind of done this recursive attribute selection, and it gets predictions by running new instances through the tree that it has made, right? And over here, just kind of like segment this visual space with perpendicular cuts, right? And then any new point, it would just figure out like what region it happens to be in. A linear model will train using a loss function, and it will try to like draw a line, right? You probably assume that the line might be somewhere like this, kind of separating these dots and the pluses. And then any new instance, we just kind of figure out what side of the line it's on. And the naive Bayes, which we covered in Friday's class just 3 days ago, it's trained using conditional probabilities, right? And we compute the probability for a new instance directly. It was just using that calculation from the last lecture. So using our final kind of supervised model, right, we're going to build a new one here, and it's pretty straightforward. So we're just going to look at it graphically first. But it's called the nearest neighbor model, and it uses the idea of distances, right? Neighborhoods are just things that are kind of close to you. So how could we use this idea of kind of distance to kind of build a new model, right? Our other models, like trees and linear models and stuff, tried to build, like separate this space into like sections, right, with lines. But we could also think about these points as being close or far apart from one another, right? So when it comes to a new point, instead of trying to figure out like what region it falls into, maybe we could just figure out who's closest to it, right? So we can leverage that idea to try to build a new model. So let's say a new point, right? Here's my data. I have a whole bunch of pluses and dots, and it's by age and balance, right? Maybe I'm trying to figure out, maybe the pluses are people that have a really high credit score, and the dots are people with really low credit scores, right? Now let's say a new person comes into my bank, and I want to figure out what their credit score might be. And they have a balance kind of a little more than, you know, the halfway point of balances, and they're a little older than the halfway age of my ages, right? And they're kind of right here. So if for this person, I just figure out who they're closest to, right? And they're actually equally as close to these 3 people, right? 2 pluses and a dot. I might say that, you know, 2 out of 3 of their neighbors are pluses, so maybe they are a plus, right? Maybe they're a plus with 2/3 probability. So the nice thing about this model, and you'll see that we're kind of doing this very quickly because there isn't really a lot of build-up to it, but the nice thing about this model is you don't have to train anything And the reason why is you don't have to train like in a decision tree and figure out all the best cuts. And the reason is because when a new data point happens, you just kind of like figure out who's closest to it, right? You don't really know who's going to be where, like what new point is where it's going to be. So you just wait until that new person enters your bank, you figure out who their closest neighbors are, and then you're done. So nearest neighbor methods are also known as instance-based learning or memory-based learning because you don't really have to do much. It's kind of like a lazy methodology. You just have all your points existing in some space and then you figure out who they're closest to. So what you do is you just store all the data you have, and then when a new person enters or a new record needs to be classified, you just figure out the distances. So a very kind of weird looking clip art version of trees versus neighbors, but a tree model would look like this, right? It's a set of rules, like you might split on age and then gender and number of credit cards. But here you just plot everyone, in this case like a 3D space, right? They'd be plotted by age and income and number of cards. And then a new person enters and I just figure out like who their closest people are, right? And I can make a prediction for them. I know the actual value for these 5 people, and my new person I don't know, so I make a prediction based off their similar neighbors. So instead of kind of using the idea of just its most similar neighbors, you'll notice here what I did was these people weren't all equally as far apart from my new person, right? They had kind of varying distances. These people were very, very close. These people were a little further. But I might want to look at more than just the exact closest people, right, to kind of get a better idea of what the neighborhood looks like. If I only made predictions about you based off of the person that was exactly close to you, right, it might be a little overfit. So I kind of want to look a little broader than that. So here I'm looking at the 5 closest people, right? Using 5 isn't like a hard rule. In this case, I might use 3 people, the 3 nearest neighbors to classify. So let's say I have a new customer, David, right? He has this age, this income, this number of credit cards, and I want to know if he'll respond to like my new credit offer, right? To sign up for a new credit card. So I'm going to use 3 nearest neighbors here. Just because that's what I want to use. I could use 4 or 5 or 2 or 1 nearest person, right? Nearest neighbor. But let's calculate this out and see what it looks like. So David is very close to himself, right? He's 0 away from himself. So the distance from David to David is 0. But now I have these other people in my data set, John, Rachel, Ruth, and they have ages, incomes, and number of credit cards. I actually know their response, right? I know if they responded to my offer. And I can also calculate their distance from David. So here I'm going to use a Euclidean distance, right? So John's age minus David's age squared. John's income minus David's income squared. Plus John's number of credit cards minus David's number of credit cards squared. Add them all up, take the square root, and this is how far apart they are. I can do the same for Rachel, right? I'm not going to walk through it, but Rachel's age and David's age, Rachel's number of income and David's income, and then Rachel's number of credit cards and David's number of credit cards, and you get another distance. I'll calculate the distance for everyone, and then I'll find the 3 closest people because I'm going to use 3 nearest neighbor. And you'll notice that the 3 closest people are John, Rachel, and Nora, right? John and Rachel kind of have 15-ish away. So is Nora. But Ruth and Jefferson are much further away, right? Like 120 or 150. So in this case, my 3 closest people are John, Rachel, and Nora. And the responses are yes, no, and yes, right? Yes, no, and yes. So for David, I might predict that he is a yes, right? So in that case, what I did was I kind of just used them to vote, right? I had 2 votes for yes and 1 vote for no between the 3 nearest neighbors. So for classification, I just used something called majority voting. For regression, like say I was trying to predict you know, maybe the response wasn't a yes or a no, but maybe it was like, how many kids they had, right? And instead of it being yes or no, it was like 1, 2, 3, 4, 5. I could take the average of those, right? Take the mean of them. I could also get probabilities out of this, right? So in this case, where I had yes, no, and yes, David might have a 2/3 probability of being a yes, right? Instead of just voting. So you'll notice that I kind of jump back and forth between just like the closest people versus like the 3 closest people versus the 5 closest people, right? And this just kind of leads us to formalize our neighborhood classifier into something called the K nearest neighbor algorithm, or KNN, the KNN algorithm. So K is just the number of neighbors to do nearest neighbor classification. In this example, I was using 3NN, 3 nearest neighbors. In this example, in this little picture here, I had 5 nearest neighbors. So an interesting call out would be when K is equal to N, right? If I had 1,000 people in my data set and I wanted to set K to 1,000, what am I doing? Right? I'm looking at the 1,000 closest people. If there's only 1,000 people in my data set, then I'm really just looking at everyone, right? So what I'm doing is I'm letting everyone kind of factor in. So if I was predicting the probability here, right, it would just be, what percentage of people in my data were a yes or a no, right? And in this example here, what that would look like is if I was using 5 nearest neighbor, right, there's only 5 people in my data set, so the 5 nearest neighbor algorithm, I don't really even need to calculate these distances because I'm going to include all 5 people. And it looks like I have 2 yeses and 3 nos. So using a 5 nearest neighbor algorithm, I would have a 2/5 probability of being a yes. Right? The other interesting case would be the 1 nearest neighbor. And in the 1 nearest neighbor, I just find the person who they're closest to, and that is the answer I give. Right? In this case, Rachel is the closest. So in a 1 nearest neighbor, I would just give whatever Rachel's prediction is, right? I would just say David is predicted as a no. And you'll notice that this is quite different, right? Like the 1 nearest neighbor gives an answer of no. The 3 nearest neighbor, the one we originally did for this one, gave an answer of yes. And the 5 nearest neighbor gives a no, right? But with a different probability. So like they're all kind of different, right? This choice of K is definitely very important. So that just leads to the question of how do I choose K, right? You won't be surprised to know that like choosing K is kind of very related to this idea of complexity, right? So in this case, I have a K of 1, right? This leftmost plot. And my K of 1 basically just says for every point, just predict its closest thing, right? So I have triangles, stars, and squares, right? And it's basically saying that like if any new point kind of entered the space and it was anywhere in this white area, its closest neighbor would be a square, right? If anything entered over here, these are a little fuzzy, these things, but like if anything entered here, its closest neighbor would be a triangle, right? Anything in this kind of like light gray area its closest neighbor would be a star, right? And you'll see that like this star and this triangle here, like this little cutoff here is like kind of right in between them because any point here would be like almost equally as close, right? You'll notice that there's a lot of like variation in color here, right? There's like a lot of little blobs of different color. But when I start to make K bigger, it starts to smooth out, right? Now I'm like letting things vote. The points are all the same. They're still stars, triangles, and squares. It's the exact same data set. But now if a point was like entering right over here between 5 and 6 and at 2, right? Like right here, it would basically find the 30 closest neighbors, which, if we look across all of here, is mostly stars. So it looks like the 30 closest would probably be stars. So it's like kind of in the star territory, right? Like if a new point was over here in the top right corner, its closest 30 is this looks like triangles, right? There's a whole bunch of triangles here, and a few other like stars and squares. So if you had to pick like which of these you think is most likely to overfit, right? Just kind of like really section out the data into these small little categories. The answer is probably one nearest neighbor, right? The smaller value of k might lead to more overfitting, right? Very granular little cuts of data. But again, the choice of k is difficult because 30 might be nice and broad, 1 might be too narrow, but maybe the value is somewhere in the middle. Right? So one way to do this would be to just try all values of k and do something like cross-validation and pick the best one. So just treat k as a complexity parameter. In decision trees, we didn't know how deep the tree should get, so we tried a whole bunch of them. We don't know how many neighbors to look at, so we should just try a whole bunch of them. Choose k using cross-validation like we've already learned, right? Just try a whole bunch of them. In most examples, this is very, very quick. So you kind of just try every value from 1 to however many data points you have, and then just pick the best one. So you might have realized that in some cases, right, the distances are wildly different, right? In the example we saw before with David and the credit cards and the ages and his, the 5-person data set, we saw that there were these people with a distance of 15 and then 2 other people with differences of well over 100, right? This is, 4, 5, 6 times bigger than the other ones. So when a new person enters, like David did before, and these are his 3 closest neighbors, but we're using, say, a 4 nearest neighbor or a 5 nearest neighbor, should we really let Ruth and Jefferson contribute as much as we did let Rachel, John, and Nora? Probably not, right? We probably want to penalize Jefferson and Ruth for being so far away. They're just so different than David, and let Rachel, John, and Nora contribute a little more. So one way to do this would be to calculate the distance like we did, right? Calculate that Euclidean distance or Manhattan distance or whichever distance you want. And then get the similarity weight, which is just, in this case, the distance squared and then 1 over it, right? So let's see if I can, So 1 over 15 squared, right, would be 0.00444. So 0.00444, right? And then we can find the similarity weights. So we basically, find the contribution. So we take all the similarity weights and then just make them all add up to 1. So you basically add them all up together and then do 0.00444 divided by that. And this should look pretty good, or at least hopefully somewhat intuitive. We have these 3 people who were much closer than these 2 people at the bottom here. And for these 3 people, right, their contribution is way more. It's like in this 30% range, right? And then Jefferson and Ruth, who are much further, are contributing 0.5% or 1/3%, right, instead of 30%. So, and now instead of just letting everyone vote, in a 4 nearest neighbor, instead of taking the 4 closest people and giving them all an equal vote, we let Rachel, John, and Nora vote with 1/3 weight, and then let Jefferson vote with a almost 0 weight. So this is just talking about another way to think about features. You could do something called normalize them. I'm going to skip over this though. Okay, so there are some issues with k nearest neighbors, right? So are k nearest neighbor models intelligible? We were looking at examples in this 2D space, right, whenever we were plotting them out. But again, once we kind of get to higher spaces, it is hard to plot, and the idea of distance isn't as intuitive anymore. You can think of the distance in 3 dimensions as being okay, right? But once you get to 4 dimensions, I don't really know what distance even means. I can't draw it. I can't really think about it. And then you have the idea of what is the distance between colors, or is the distance between 1 or 2 or 3 children the same as $1 or $2 or $3, right? Probably not. And it's hard to figure that out. You also need to think about like what distance metric to use. Like, why did you use Euclidean distance and not Manhattan distance or not cosine distance? And again, there is no real good like decision. You just kind of like pick one and go with it, or try a whole bunch of them and test them out. But explaining why you did that can be difficult. There may be too many attributes, right? This idea of distance kind of breaks down if you have thousands or tens of thousands of features. It's hard to really visualize what distance between things are. One way to do this would be kind of get rid of some attributes or get rid of some features and clean them up, but that's a topic for another class. Computational efficiency, though, there's no model training, so it's very, very, very fast, right? But you need to keep all of your training data around. Like, you can't just train your model and then get rid of it. You have to keep it around because you need to calculate the distance every single time a new instance enters. So to kind of like throw them both, all of our models that we've ever learned, kind of like on a screen here, we focused mostly throughout the semester on linear and tree-based models, right? Where linear models kind of make these nice perpendicular cuts. Where tree models make these perpendicular cuts and linear models make one single line, right? Nearest neighbor models let you draw arbitrary boundaries that can be curved, they can be separate, they can be just like little islands and stuff. So it looks quite a bit different, right? You can draw more than one line and you're not bound to perpendicular cuts. Okay, so the kind of overview or the recap of our very last supervised model of the semester would be, in a nearest neighbor algorithm, what you want to do is just find things that are similar in some ways, and then assume that they're going to be similar in other ways, right? If you, like before we were looking at similarity in age and income and number of credit cards, and we were assuming that that similarity kind of mapped to their similarity in response to a new credit card offer, right? That yes or no question. But you have quite a few design decisions to make. You have to figure out like what distance metric to use. How many K, right? 1 nearest neighbor, 10 nearest neighbor, 100 nearest neighbor. Should you like treat all points as, kind of equally contributing, or should you weigh them by how far away they are? Again, there's a whole bunch of decisions here. No one decision is right. People, again, often try many different decisions and test them all, and they just figure out which model fits the best. And you don't really train a model. You just kind of like keep your data around and then find distances every time you need to. Okay, so I want to jump into now unsupervised learning, right? So we kind of finished up and we talked about this very last supervised model, this K nearest neighbor model, but now I want to kind of shift over and talk about unsupervised models, something we haven't talked about basically at all this semester, and kind of introduce you to it right now. Okay, so as a reminder, supervised versus unsupervised models. In supervised data mining, we're kind of like basing it on the well-defined target variable, right? Supervised, we have a target variable we want to predict, and we use training data that includes labels for that target, right? You want to predict if someone's going to be admitted to the hospital or default on a loan or buy your product. You need to have data where you know if people have done that thing before, right? This is something you're doing in your projects. It's what we've talked about all semester. On the totally flip side of that would be unsupervised data mining, which basically means we don't have a target variable. We often use this to explore data. And, this might seem like it's not as useful, but in reality, like unlabeled data is so much more common. There's data everywhere. And then to think that it all has like a very clean target variable that you might care about is probably kind of silly, right? You could look at any data set and think of any number of things you would be interested in learning about it where you don't have a clean target variable. And we'll look at some examples. So the key idea in unsupervised learning is that we're trying to find groups of instances or records that are similar to one another, but are not similar to instances not in their group, right? It's kind of weird, but we'll show you what these look like in a second. So what is unsupervised data mining good for? It's good to understand the natural grouping of items. It's super useful if you only have a few labeled examples, right? You only have a few records in your data set where you know the value for the target variable. And this might help you label new ones where you don't know the answer. If you have no labels at all and want to figure out labels, like maybe you have the tasting notes of a whole bunch of wines, right? But you don't really know what the target variable is. This could kind of help you find it. And again, we'll look at examples of this. It might not be super clear now what I mean. And we can think about this as doing feature engineering. And I'll see if we get to this at the end, but we might not cover this topic. So some good examples of unlabeled data sources. We have tons of text data, right? Like, so for example, news stories. You might be interested in determining whether or not a news story is happy or sad, but like newspapers don't tell you that, right? Like you don't have a clean target variable for that. You'd have to figure it out yourself. You could read the news articles and decide, right? But it would be super cool if we could automate that process, right? For blog posts, maybe we're interested in categorizing them into some number of categories. Maybe people talk about their vacations in their blogs, their families in their blogs, and then their hobbies, right? And they don't tell you what any one article is really going to be about. It would be cool if we could automatically tell them, right? Be like, hey, here are all of your hobby articles. Here's all your family articles. Here's all your vacation articles. And a whole bunch of other examples. So when we think about unsupervised models in the kind of world that we've looked at so far, the business understanding phase where we often start and we try to define like a very clean business problem, we just have to be a lot more creative to define a good problem. It's not well formed because we don't really know much about the data. We don't have a target variable. There's like no one clean thing to predict. So we have to be a little more creative. All of the models we've learned so far do not apply, right? We can't use trees, we can't use logistic regressions, we can't use linear regressions, we can't use SVMs or naive Bayes or KNN, right? We've learned 6 models so far, and none of those 6 models apply to this type of data because we don't have a target variable. And then in the evaluation phase, where we learned how to do like cross-validation and test train splits and look at accuracies and ROC curves and all those cool things, right? They don't apply anymore. Evaluation in an unsupervised setting is very, very difficult and sometimes impossible. And we'll look at some examples and you'll see why they are so difficult. So the first kind of unsupervised model we're going to look at is clustering. And the idea here is, how do I find groupings of similar objects when I use my data to describe them? And we're going to, it says, it's a little technical. When I show you a picture in the next slide, I think it'll become more clear, but I want to minimize intra-cluster distance. So I want to find points within a cluster that are very, very close, but I want to make sure that my clusters are far apart. Right? And we'll look at 2 different methods for clustering. Okay, so here's that picture that I was promising you here. In this example, I have data that's defined by 2 features, right? X and Y, and I've plotted them all. And I am looking for 3 clusters. We'll talk about how to pick the number in a second, but basically I found this like red cluster where all these red points are kind of close to one another, right? These green points are all close to one another, and these blue points are close to one another. But you know, the red points are generally further from the green points than they are from themselves, right? These blue points are a great example. They're like all very close together, but not close to the green and the red ones. And you might be asking, well, it kind of looks like this green and this red cluster should just be one big cluster, right? Why did you separate them into 2? And this is where part of the problem comes in. We don't really know why we separated them into 2 clusters instead of one big cluster, right? And we'll talk about why a little later. This other type of clustering is hierarchical clustering, and it kind of looks like a decision tree, but it's not. This, I think, like the best example and one you're maybe all familiar with would be kind of like this, the animal kingdom, right? And we know that like in biology, we kind of like segment animals and partition them into these like little categories where based on evolution and how related they are. But these are clusters, right? Like there's the dog cluster, the bear cluster, and like the cat cluster. right? These clusters make intuitive sense. A human made these up, right, using like biological data, but a human made these clusters. And we're trying to think about like a way of letting a machine do this as well. So to get to this type of cluster, right, this hierarchical cluster, we can use an algorithm to do so. Let's pretend that we had a few different points of data, right, points A, B, C, D, E, and F. And what we do is we find two instances that are closest. So pretend these red circles didn't exist, right? A and C are definitely the two closest points amongst all of them, right? E and B are a little close, but not as close as A and C. So merge them into one cluster, right? Step 2. And treat this new cluster as a single instance. Instead of it being 2, we're just going to treat it as one instance, right? Just kind of like right in the middle. Now repeat steps 1 and 2 until all instances are in a cluster. So if I consider this to be kind of like the instance AC, right? This is just one instance. Which two instances, this new one, B, E, D, and F, are closest, right? It kind of looks like E and B are the closest, right? So we'll kind of put those in one cluster. Okay, so now I really only have 4 points, right? I have this one big point, this new other big point, and then D and F. So now which 2 points are closest? It kind of looks like D and this new point I just made are closest, right? So I'm going to put those in one cluster and then start all over again. And it's kind of hard to see, but it does look like this new cluster is closest to this one. So I'll put that in cluster 4. And I really only have one thing left to do, and it's to bring F in, right? So now I have one big cluster. And I can kind of draw this out. The book does a better job at explaining how this process works, so you should definitely check it out. But you'll see that I made A and C as my first cluster, right? B and E was my second cluster. And then B, E, and D was my third cluster. And then I brought them all together for my fourth cluster, and then every single point together for my fifth cluster, right? And this is just looking at the distance here. Like the distance between A and C was 0.03 or something, right? The distance between B and E was 0.06. The distance between this new cluster and D was like 0.1, right? And it's interesting, like I don't really know how many clusters I should pick. So you can cut across here and basically pick as many clusters as you want. If I were to cut along here, I would have 5 clusters. I'd have this one cluster of A and C, and then B, E, D, and F in their own individual clusters, right? But if I decided to cut here, I might have a cluster AC, a cluster BE, and then a cluster for just D and F, right? And this is like subject to how you want to view it. Like how many circles do you think are too many? It's very hard to decide. It often depends on your use case, and we'll see some examples of trying to explain them, which might make it clearer. So here's another dendrogram, it's called. This kind of hierarchical cluster. We put it together in a dendrogram. So here's another one, and this is on the whiskey data. So I did the exact same process. I plotted all my whiskeys and all their tasting notes, and I just built clusters, right? I'm sorry, these aren't whiskeys, these are beers. So it looks like Heineken and Corona are in their own little cluster. These 2 Sam Adams beers are in their own cluster, right? This kind of makes sense, right? Sam Adams are together. The Guinnesses are all kind of together-ish, right? Guinness and this original Guinness are closer to one another. These like more specialty Guinnesses are here. The draft Guinness is a little separate, but they all kind of fall into this one cluster. Stella and Blue Moon, I could kind of see that. But again, there's a whole bunch of beers here. And remember, I was saying, like, you know, what does it, like, this one big cluster, right? If I look at the very, very top, this one big cluster is, like, just beer, right? But that's, like, useless to everyone. So, like, maybe I want to cut it here. And maybe I have a cluster of, you know, like, import beers and, like, very popular barbecue beers and, like, I have no idea what any of these beers are. So I'm going to say the beers I don't know. are in another cluster, right? And you just kind of have to figure out like where you think it makes sense to draw the line. And you'll see that this isn't very scientific. Like I am trying to apply some human aspect to this, like to say that this is the import section, right? And this is like the barbecue beer section, because I don't really know any better. Like that's just what I think the answer is. And that's a big part of unsupervised learning. So like how to formalize that, like how do I actually use this? You kind of just manually pick, right? Like it's one way of doing it. Like you might just say, hey, this is like, these look like they're kind of similar. I'm going to call this a cluster. Or maybe you figure out where to draw the line to figure out how many clusters you have, right? And again, you have to do this and then interpret them and see if they make sense to you. And it's not always easy to do. It's not always possible. So we can introduce an algorithm that helps us build clusters in another way, right? We talked about the hierarchical algorithm, and now we can talk about another algorithm, and it's called the k-means algorithm. And the way it works is it randomly initializes some number of center points. It finds all the points that are closest to it, and then it just tries to do that thing where it tries to minimize the distance within the cluster and maximize the distance between clusters. So I'm just going to jump to this video. Okay, so in this example, you'll see that they made 5 clusters, right? They set k to 5, and they have 1,000 points of data here. And if you notice, they like pick these like center points, right? Like a center point here and here and here, here and here, and they're just finding like which points are most closest to it, right? And they just keep stabilizing, and they keep iterating until it stabilizes around 5 clusters where all the points in the cluster are closest to that cluster, and all clusters are far away from each other, or as far away as they can be. Now, this is like a very similar data set, but here I'm going to ask for 10 clusters and see what happens, right? Again, kind of looks the same, right? We have 10 distinct clusters where it's just really the most similar points. And this might not look as interesting because we don't know what these points are. We don't know if they're food or people or something, but this is all the process. This is all the process does. Here it is for 20 clusters. Here's 5 clusters, but with more data, right? We have these like nice, clean little boundaries. Here it is for 10. So you can check this video out. It goes through a whole bunch of different examples. Okay. So why might I want to do this? One pro to the k-means approach is that it applies to like very large data sets. Like you can do this with any number. We saw it happen very quickly for 1,000 data points, 5,000 data points. It works fairly well on various sizes. And it converges to some kind of optimal value. So it will find some value that it does ensure this claim that the points are close together, but the clusters are far apart. And it generally creates clusters that are relatively uniform in size. You'll notice before in that example, right here, that like it's roughly the same number of points in this blue cluster in the bottom left as like this orange or pink cluster. Maybe this is a pro, maybe not, but it is very different than this hierarchical clustering, right, where these clusters had various different numbers in them. So it really depends what you're looking for. The cons are that it's sensitive to the initial point. You'll notice that I'm randomly picking the cluster starts, and I just did that at random. And if I chose a different randomization, it might find different clusters. So you'll see that if you do clustering over and over again, you'll find different ones, which is not always easy to explain. And the number of clusters you pick, like in this example, I picked 10 clusters, and earlier on I was looking at 5, right? It's not always clear if you should pick 5 or 10. You just have to kind of pick various values and see if it makes sense. Okay, so say you did clustering. How do you actually evaluate that it is working, right? How do you evaluate whether or not you should have picked 5 or 10? It's very hard, and it is a little more of an art than I think a lot of people like to admit. But there are some ways of doing it, right? And there are like these two kind of popular ways. There are two popular ways to evaluate clustering. And the first is an exemplar. So you would pick the most famous or well-known value in a cluster. I think we'll see an example in a second. Or you can pick the average, right? So you might, if you have 10 people in each cluster, you might take the average age or income or something in that cluster and kind of define it that way. But is the clustering any good? Literally no idea. And you'll kind of like never know. This is why it's not always super fun to do unsupervised learning, and I highly suggested to not do it for your projects. It's because it's deeply unsatisfying often because you don't know like whether or not it's doing a good job. So I kind of introduced these two approaches, hierarchical clustering and k-means clustering. And they have a few differences, right? We can think about hierarchical clustering as trying all possible number of clusters, right? If you remember like those dendrograms, right? I first consider the case where every single point is its own cluster, and then I start building different sizes of clusters, right? I start merging them together to build that kind of like tree structure. So it tries all possible ones, and you can pick where you think the best split is. But for k-means, you need to predetermine how many clusters you want. Hierarchical will try all like possible values. K-means you have to say, I only want 5 clusters, or I only want 2 clusters, or 10, or 100. And then you have to evaluate it after the fact. However, evaluation is hard for both. You really need to be a subject matter expert, right? Like in the beer example, like I don't know much about beer. I know a lot more about scotches, but I don't really know like if this clustering makes sense, right? I want to say it kind of does because like all the Guinnesses happen to be together, and I feel like that's probably accurate. But someone who knows more about beer than I do, like definitely take a look and see like are things that are kind of paired together or grouped together. Does it make sense to you, right? Does it like feel like those beers are similar? Would you be fine making a recommendation based off of that clustering? And like, where would you cut the line here? So you need some kind of like subject matter expertise often to evaluate if clustering is doing a good job. Okay, so another way of kind of using unsupervised learning is to do something called dimensionality reduction. There's a few use cases for this, but basically what we want to try to do is reduce the number of features in my data set. And to do this, I'm going to try to figure out if any of my features are related to one another in some way and figure out some like underlying explanation for it. It sounds kind of weird, but the idea is, if you had a whole bunch of features about hobbies, right? Like, whether or not people were interested in soccer or football or hockey or baseball, you might find some latent idea, right? Which is really just, are you interested in sports, right? Like maybe you can just summarize those 4 features, right? Interested in baseball, soccer, football, or hockey, and just have one feature called interested in sports, right? That's like a latent idea. The latent idea is sports. The things you actually observe are the actual sports themselves, like the hockey or the baseball, right? Can we figure out this latent part to it? And the technical way of doing this is through something called matrix factorization, which we will not discuss in depth. But there's some very popular methods for doing this, like SVD and PCA. But again, we won't talk about them in this class. So why should we really care about dimensionality reduction? Data sets are very, very, very big now. The Netflix Prize dataset, which we'll talk about in a few slides, we'll do like a little example. The Netflix Prize dataset has 500,000 users in it and 18,000 movies, right? 18,000 columns of data, whether or not someone watched a movie and what they rated it. That's a lot of movies. That's a lot of features. All of those features together might not be super indicative, right? But if we could try to find latent dimensions, like maybe themes of movies, right, or categories, or like, similar director styles or something, we could probably cut down this 18,000 movie titles feature set into a more manageable chunk, right? Like genres and directing styles and film style. Just make it, a little easier. We have this other, the other end of the spectrum, like in banking data, you might have a few million customers. In this example, we have, a little bit more than 500,000 customers, but we have 2 million payment receiving institutions like stores and stuff, right? We have more payment receiving institutions than we have customers, right? That all the data sets we've ever looked at have always been like longer. They've had more people in them than features. But here we have way more features than we have people, right? That's a lot of data. Can we cut down that 2 million payment receiving places into a much smaller manageable value? In online data, this gets even crazier. Millions of rows and millions of websites. That's just a significant amount of data. So what is a latent factor, right? I talked about it as this like underlying attribute. But each latent factor can be interpreted as representing some underlying, it's kind of weird to define something with the word itself, but some underlying aspect or feature in the data, right? I talked about like this idea of sports being a latent dimension for a whole bunch of different, activities like playing soccer or interested in football or interested in baseball. Like sports is the underlying latent feature. It's related to clusters, but like some more examples would be like in 100 movies as features, we might have latent dimensions that are genres. If we have a whole bunch of features related to like people's incomes and like neighborhoods and stuff, we might have some latent factors such as like their socioeconomic status or the actual like neighborhood they live in. However, while these interpretations seem nice, right, like going from 100 movies to genres sounds great. I would love to be able to do that. When we actually do uncover these latent factors, they're usually very hard to interpret. So this is useful just because it helps us like cut down the size of our data sets. It's also very useful for recommender systems, which we'll talk about in a little bit. So one interesting example of this would be the idea of what we call eigenfaces. So eigenfaces just really is one way of like kind of showing like facial data, right? So like in this example, we have a picture of a person, of a man. This is very blurry, I'm sorry. But we could take this feature or this picture and represent it as a set of features where each feature here is the pixel color, right? Like from white to black and all the grays in between. And you'll see here that I'm like kind of identifying each little pixel, right? And it's k pixels by k pixels. So I have k squared features. I'm going to write them as rows here instead of a column, just because I run out of space on the computer or on the screen, so bear with me. But this one record, this one picture, is represented by k squared features, where these are just the grayscale number for each pixel. I can take a whole bunch of pictures, right? Here's a whole bunch of records. It looks like I have 2 pictures per person, 1 or 4 pictures per person, but just different facial expressions for these people. And if I have n people, I'll have n faces and k squared features, right? So just like the pixel values for each face. So if I apply this idea of latent factors, which we will not really talk about how we get them, right? But if I take the top 20 latent factors, this is what it looks like, which is kind of weird. They kind of have the idea of faces, right? But what this is saying is I could take hundreds of real faces, and store them in just 20 faces, right? 20 summaries of faces, creepy summaries, but 20 latent factors, latent faces. And what's cool is I can actually represent any face in my data set using just these 20 faces, right? So like if I had a picture of me, sorry, this thing keeps popping up, but if I had a picture of me, I might be 90% of this top left eigen face plus 30% of this face, and then, I don't know, 11.2% of this face, and some percentage of all the other faces. And if you literally add them all up, you would get like a picture of my face, right? And this is super cool because this just means that instead of storing hundreds of faces on my computer, I can just store 20 faces and then a few numbers. 20 faces and 20 numbers, I can represent any face in my data set. Right? And it's kind of cool because you could try to think about like how to describe each of these things. Like one of them might be like the hairstyle latent face, and one of them might be the nose shape latent face, right? It's a little hard to interpret here. There's definitely something about like people wearing glasses, it looks like in this one, like the glasses latent face versus nose shape maybe in these ones down here. But just latent faces. So I think this is a pretty cool example. Another way of thinking about this, or another example of this, would be something called topic modeling. So if we have a term document matrix, this is like the thing we talked about on Friday in class. But if we had a data set where we had documents as records and then words as columns, we could perform one of these latent factor analyses on this massive matrix and look at just a few of the latent dimensions. And this turns millions of dimensions, millions of features, millions of words down to just a few, maybe 100 dimensions. Right? So like an example of this would be, in this example here, I took the TASA corpus, so just a collection of documents. I forget what this is about. I think it's something to do with like legal trials. I can't remember fully, but it's just a set of documents. And I don't really know anything about them other than the words that are in them. But I ask my analysis method to go through these like millions of documents with their millions of words and just pick 300 latent dimensions. And then I just picked 4 of them here to show you. And these are fully built by the computer. The computer doesn't know anything except what words are in what documents. And it kind of looks like it came up with categories, right? Like in this one here, it looks like it came up with a category for like medical things, right? Like doctors, patients, nurses, medicine, dental, physician, right? It came up with this idea of like there's a topic that is made up of these phrases, right? And it would be interesting to see, can I then go in and say, hey, any document that kind of like uses most of this latent feature to represent it is probably a document about medical things, right? This one here is about color, it looks like. This one here is about drugs or medicine. So you could take millions of documents, and in this case, you could kind of come up with categories. You'll notice there is no category name, right? It's just called topic 56. You have to use some kind of human element to evaluate this. Does this make any sense? And in this case, I might call it like the medical topic. It's definitely possible that you have a topic where all the words like don't look like they have any common trait to them, which is fine, but just harder to label then. So the takeaways here is that unsupervised learning is useful for exploratory analysis, right? Like this idea of like, are there any categories in my documents, right? Are there any kind of similarities in faces? And we looked at a whole bunch of examples just a few slides ago, right? Are there any like trends in my beer data, right? Like maybe I should design my store that way, or like set up a shelf for each kind of segment of beer. And it also helps me cut down on my number of features, right? Like again, these examples here let me cut down millions of words, just a few topics. So it let me cut down features and maybe prepare for some other kind of supervised learning if I have a target variable, as well as helping me explore stuff. I could find natural groupings in my data. like the beer example. And we learned a few different methods here. So like this idea of hierarchical clustering, or we looked at the kind of the beer cluster, k-means clustering, and dimensionality reduction. Right? These are like three kind of models, of unsupervised models we've looked at. You'll notice that none of them have a clear evaluation, right? It was very human-based, and none of them had a very clear target in mind. We were just looking for cool stuff, which is not always the easiest thing to do. I want to take a quick look at a hands-on that kind of talks about an unsupervised approach and kind of shows an example that you can actually play around with yourself. It's pretty fun, although the data is a little bit old. So to do it, you can grab the latest hands-on material. This is actually the last hands-on we're going to do in class. If there's interest, we might talk about it in like that one class we kind of have set aside for special topics. But otherwise, pause the video, grab this hands-on material and open it up in Anaconda. I unfortunately broke Anaconda on my computer last week, right after I broke it on the computer in the classroom for those who were there in class on Friday. So it's going to look a little different on my screen, but it will work just the same for you. Okay, so let me just jump over to the hands-on. Okay, so again, like I've always said all along, basically don't stress out if you don't fully understand all the code that I have here. It's a whole bunch of helper code, but I really just want to get the message across of like what we're trying to do. So I'm going to start by running these first few cells of code just to like import some useful things. Now, I want to bring in some data, and I have some data about movies. I have rating data about movies, and I forget where this came from. I think it came from IMDb, but I don't fully remember. But it's just a list of movies and how they were rated. And we're going to use that to kind of like look at clusters or explore our data. Okay, so I'm going to import that data. Now, what I'm going to do is I'm going to use this idea that we just talked about of matrix factorization, and I want to take all of the examples of our data, right, which is a whole list of users and a whole list of movies as rows and columns, and the ratings, which is a significant number of features, and I want to reduce that to some number of latent dimensions. And we'll talk about in a few slides like this idea of pulling latent dimensions out of movies. So you'll see it in a second when we do another case study in a few slides. But this idea, again, of latent dimensions, right? I'm trying to summarize my list of movies or my matrix of movies and ratings as having some latent thing, which might be like genre or some other kind of concept. And in this case, I'm going to just pull two of them. And the reason I'm going to pull two latent dimensions is because I want to plot them. So with only two components, it's super easy to visualize, right? Something we said all throughout the semester. I can look at it on the X and Y axis. And this is what you get. It might not look super pretty. We really don't know what we're looking at. But basically what this is each dot is a movie, and this X-axis is some latent component. I really don't know what it is. It might be something like genre. And this other component too might be something like style of movie, but in reality it could be some latent thing that a human being couldn't interpret. But what it lets us do is plot things easily, and hopefully these latent dimensions mean something such that things that are close together, movies that are close together, are actually similar. So to see if this is true, I'm going to just take a look into my movies and just find the movie X-Men. It looks like I have a few different X-Men movies in my data. It looks like the original X-Men movie has an ID of 74 or 78. And I only did that so that I could put it down here. If you change this number to any ID in the data, it will show you that movie. Okay, so let's take a look. So if I plot my components and just look at X-Men, it just puts X-Men in the middle. And then it looks at all the movies that are around it. And it's kind of interesting. But it looks like X-Men in the middle, and then like up and to the left is like action-y kind of movies, right? Like there are two X-Men movies, the Watchmen movie, Fast and the Furious movies, Some Mission Impossible movies, right? I could kind of see this, right? This idea that these X-Men movie cluster, this kind of action-y, superhero-y cluster, that looks about right. I have no idea why Hotel Transylvania is near X-Men. Maybe there were some like movie, some actors, some movie stars that were in common between the two. But another example, like, see up here, it says Harry Potter and the Sorcerer's Stone. It looks like right next to it kind of is another Harry Potter movie. So maybe there's like some kind of like, fantasy trend here, or something about movies and how they're similar. Like maybe this x-axis, this latent dimension, is something with like movie stars, right? And maybe these movies have a lot of people in common. You can type in any movie you want here. Like I said, the data set is a few years old, so not every movie is in it. But is Iron Man in here? Yeah, so Iron Man, and then we can put the Iron Man ID in. Iron Man, Thor, X-Men movie, Kick-Ass, which I could kind of see. It's kind of like a comic booky type movie. Taken 2, not sure why that's in there. Again, not really sure why the other Iron Man sequels aren't in here, but we don't really know what these latent dimensions are, right? But some of the neighborhoods make sense. Let's look at one more. The Lord of the Rings. So let's put the original Lord of the Rings in. Or well, that's a really old one. This is actually a really bad cartoon. Let's look at the Fellowship of the Ring. So 74:18, and this will be our last one. So Lord of the Rings, Star Wars. I could kind of see it, right? But again, are these latent dimensions useful? It's hard to tell. Like this is part of the art of the unsupervised thing. I build these latent dimensions by using matrix factorization, but I don't know if they're useful, right? You have to kind of figure it out for yourself. So feel free to check out some other movies, take a look, see if this makes sense to you. Yeah. Okay. And then the last thing is you just want to make sure you save it and then go to File, Close, and Halt so you don't lose the notebook. Although, again, if you ever do, you can always just check it out by downloading it again. Slides. I just want to kind of step back and think about a case study that uses a lot of different data science concepts that we've kind of covered already. This isn't necessarily related to like the unsupervised learning or that last supervised learning method that we learned today. It's kind of like a collection of everything. So I'll kind of go back and forth between the two terms because it was, this example of recommender systems is going to be fairly complicated and kind of touch on a lot of different aspects of data science. And you'll see what I mean when I kind of show you the scope of this thing. A lot of the details might be very technical. Some of it will be stuff you've heard of before. I might just go into a little more detail. Some of it will be stuff you haven't heard of before, which is totally fine. I just want you to see the scope of how complicated these problems can be and just how many people and how many decisions go into things like this. And we're going to talk about this through the idea or through the example of the kind of Netflix data question. So again, if you have any questions, if something seems super crazy, it might just be because we haven't really talked about it, and it's totally fine. Like you're not expected to kind of like know how this case study works. I just really want to show you what it looks like. But again, definitely raise questions within the discussion board or just shoot me an email and we can chat about them. I'd be happy to talk more about really any of these topics. Okay, so I'm going to look at this through the example of a recommender system. And specifically this idea of matrix factorization, which is kind of the idea we briefly talked about in the last section where we talked about like latent factors and stuff. Like that kind of, a lot of it comes out of this idea or use this idea of matrix factorization. We didn't talk about the technical details of it because it's a little more like linear algebra than this class requires you to know. We'll talk about it very briefly in a second. I'll like paint a very high level picture of it, but it is very important. Bell and Corin are two super big names in the recommender system world, and they found when reviewing different examples of recommender systems that matrix factorization was kind of found to be super accurate and was very popular. Okay, so how do we start building a recommender system? Well, one way we'll do this, right? We're going to use this like idea of a data set about movies as our use case. And here we have a data set of movies, and then the people who have watched them, and then the rating they gave it from 1 to 5 stars, right? And we're going to use matrix factorization to kind of like get a better understanding of this. And you'll see what that better understanding looks like when we get to the end of this picture, but just bear with me. One thing to notice though is that these empty like cells are not because the user rated it a 0, it's because the user didn't rate it, right? Which is different. Like here a user chose to give movie 2 only 2 stars, right? I don't know what user 3 would have given them. We don't treat this as a 0 because maybe if they had watched the movie and rated it, they would have given it 5 stars, right? Like I don't actually know what this value is. And that's important because that's how we can help make a recommendation, right? Like should we recommend movie 2 to user 3? Well, if we think that this kind of rating would be high, right? If user 3 would rate this movie high, then maybe we would, right? Like maybe we would make a recommendation. And that's kind of like what we're going to try to do here. Is we're going to try to fill in these empty values. So the way to do this is to decompose this matrix, right? This matrix of movies and users and their ratings. And we decompose it into 3 different matrices. I won't really talk about how these are made, but we call them the U, sigma, and V matrix. And we decompose it into 3 matrices using a linear algebra equation. And we take these 3 matrices. We just take a few latent dimensions. And all that really means is we just take, in this case, 2 latent dimensions. So we take 2 columns. We take 2 columns and 2 rows, and then just 2 rows. There's no reason for you to like expect this to be the case. Like, why am I taking 2 columns here and 2 rows here? It's just how the matrix algebra works out. But you can just take my word for it. If I wanted to take 2 latent dimensions, I would just take 2 rows, 2 columns, 2 rows, and then 2 columns and rows of this middle one here. If I just take 2 latent dimensions, right, I'm not taking all of the data that I have. I'm just taking 2 kind of high level or deeper understanding summaries of my data, right? This would be trying to get at the whole, like, you know, maybe a whole bunch of my columns in the original data are talking about different movies, right? Like movie 1, 2, 3, 4. But maybe this first latent dimension is something to do with genres, right? I don't know if that's true, but that's the idea. The idea is that like I'm hoping that this one is like some high level representation of the movies, and maybe this one is like director style or something. Don't know if that's true, right? But that's the idea. I'm trying to take a high level summary of the data. And what that then lets me do is rebuild my original data set. So I take my original data set, I decompose it, I take 2 latent dimensions, and then I multiply them together. And when I multiply them together, I fill in all of my empty cells, but also all of the cells that I already had filled in, right? So you'll notice that originally I thought this movie was rated a 5 by user 1. But now when I rebuild it, it looks like user 1 rated it 4.9. And that's because I am dropping some of the additional detail by only taking 2 latent dimensions, right? So I'm not going to be able to perfectly predict or perfectly recreate the ratings that other people had. So like user 2 and movie 2 had 4 stars. Here I'm a little off, right? I'm saying 4.5 stars, but it's just going to be a little noisy. But the benefit is that it now gives me ratings for things I didn't know before. So now it thinks that like movie 1 and user 2 is going to have 4.1 stars, right? Originally I had no idea. User 2 didn't rate movie 1, but now I can make a guess, right? And it looks like, you know, for example, user 2 would rate hold on. Yeah, so user 2 would rate movie 1 4.1 stars, which maybe is pretty high, right? Maybe we should now recommend movie 1 to that user. For user 3, where they didn't rate any movies, right? Now I have, they would have maybe rated movie 1 2.2 stars. It looks like 3.8 for movie 2 and a few others here. But if I wanted to pick one movie to recommend, maybe I would recommend this 3.8 one, right? And it got this by learning some latent dimension of my data, like something about the genre and director style and artistic design of the movie or something, right? And it used that to figure out what the prediction would be. So this is kind of the workhorse of recommender systems, this idea of latent dimensions, right? This isn't like a supervised approach. This is unsupervised. I don't actually know what the answer for these new users would be, right? But I can try to build some or discover some latent dimension. So why does this work? Again, it just kind of captures these latent dimensions, something like genre or style. And it determines how people would rate on this dimension, right? Like, how can I recreate the dimensions just using a few of these? I'm sorry, how can I recreate a rating using just a few of these dimensions? All movies will contribute in some way to some latent dimensions. So like I'm taking that overall, like this overall picture of movies, and I'm getting some latent dimensions from it. It helps me fill in the blank ratings, which is super useful when it comes to recommending new movies. Again, this is just, reiterating the fact that like a blank rating is actually blank. It is not a 0, right? We don't actually know anything about it. So how do we deal with those null values? This method we used called SVD stands for singular value decomposition. There are methods that they work very nicely with these like kind of empty null values. So we just use a method like that. And it statistically uses a specific method, which we won't really talk about. Okay, so let's look at an actual use case of this. So we could think about it, we can think about the Netflix prize as our use case, where we have a data set of roughly 6 years of Netflix rating data, which comes out to about 100 million ratings for a few 100,000 users and almost 20,000 movies. So when we think about what the Netflix prize was trying to do, it was Netflix trying to make their recommendation system better, right? So what they did was they actually did a supervised problem, kind of, where they knew for some set of users what the rating they gave was, and they held that data set out and said, hey, researchers, can you recreate this rating, right? Can you figure out what the recommended rating would be for these users? And if you got a 10% improvement over Netflix's recommendation system, you won $1 million. So I took this from this blog post down here. This goes into a ton of crazy mathematical detail, which we won't really cover. But the main approaches fell into a few different categories that tried to answer this problem. Some of them were matrix factorization approaches, like we kind of talked about. Some were regression approaches, right, just trying to predict star ratings. I'm going to talk about some of the neighborhood models, like the ones we just talked about. I'm going to talk about all of these very, very briefly, just to give you an idea of them. But safe to say that like when these were used in the actual competition, they went into a ton of detail. Okay, so the kind of like first approach that they use here is this idea of global effect normalization. Again, this is just one of many things they use, but basically the idea is we can take any one like movie rating, right? So like say I rate the movie Inception and I give it 4 stars. We can break that down into a few different pieces. So basically, maybe overall, all movies on Netflix get a 3.1 stars, like on average. We just average all stars for all movies together. I tend to rate movies a little harsher, right? I tend to give movies 2.5 or 2.6 stars. So I'm really subtracting 0.5 stars from the global average, right? However, the movie Inception tends to get like 3.8 stars. So it does like 0.7 better than the global average on Netflix. And then my interests versus Inception's interests kind of add another 0.7 stars, right? Which is how I get to my total 4 stars. If I normally rated things 2.5 stars, Inception being such a good movie and my kind of interest in those topics is what brings my 2.5 stars to, roughly 4 stars. This is a little harder to explain or harder to wrap your mind around, but we could think about there being like the me component and the just Netflix component and the movie component. And the hard thing is like this interaction. Like, how do I actually know that I will like Inception so much that I'll give it some positive number of stars? So this is the kind of thing that we are trying to predict. So matrix factorization is another approach that they would use to try to tackle this Netflix problem, and they did use a lot of. And what it tries to do is use matrix factorization to capture some latent features of the whole movie data set that can be used to fill in the blanks that we didn't have, right? We already talked about how to do this. Another idea, which is kind of getting at something we talked about, is the use of neighborhood models, right? We can find movies that are similar to other movies and users that are similar to other users and use those similarities and distances to, come up with new recommendations. So one example of a distance metric we might use is the Jacquard distance, which is, if you remember from a few slides ago, is those kind of 2 shopping baskets of different fruits, right, from the supermarket. In this case, each shopping basket can be the number or the movies that I've watched, right, and the ratings I gave them. And if I take 2 different people's shopping baskets or 2 different people's movie watching behavior, I can take the Jacquard distance or like the kind of overlap of those 2 ratings and figure out if I can predict for new ones. We have to choose the K closest movies to any unknown movie. How do you choose K? You can use cross-validation. And then we can combine all the ratings for similar movies and get a predicted rating. We could use regression, something we've covered in class already, right? We could take a whole bunch of movie features, like the year it came out, the genre, if it was a hit at the box office, if it made back its budget, number of awards it got, how many actors it had that have won awards. And it could also take stuff like, how many movies does a user watch if they've also watched this movie? Number of movies in this genre that movie is watched. And I can just apply regression, right? Take all those features and try to predict stars. And then apply that model to movies where I don't know the rating, right? Don't forget, you have to regularize and figure out how complex your model is, but you just choose that through cross-validation. Okay, this is another method that was used by the people that were trying to solve the Netflix rating problem. This is something we've never talked about before. It's called a restricted Boltzmann machine, and it's a type of neural network. So people who are super interested in AI stuff, this is, a kind of like very AI-y type model. But it tries to break down movies into these idea of like hidden units or like hidden neurons. We won't really talk about how this works, but if you want to check it out, you can check out Edwin Chen's blog post for more details. Another approach, and the kind of like last one we'll talk about, is this idea of ensemble methods, which, if you kind of like think about what the name means, should hopefully be somewhat self-explanatory. But basically what you do is you train all types of models. Like you train the restricted Boltzmann machine and a regression, and you do matrix decomposition, and you do neighborhood models, and you do all the other things we talked about. And you take all of those models and you just combine them together. So let's take the 4 models that we've already talked about, like a tree, a matrix factorization, a regression, and a restricted Boltzmann machine. Let's ask each of our models what the new star rating would be for any given movie, and then we'll combine all their ratings. We could run another model, or we could just like take the average of all of those ratings from the 4 different models, right? And if this combined prediction, the idea is that it kind of gives you the best of all the models, right? Like it might give you some interesting thing that the decision tree has learned and some interesting thing that the matrix factorization model has learned and the lasso regression and the restricted Boltzmann machine, right? They all have pros and cons to them. And if we combine them all together, the idea is that we can try to get the best of everything. And the super cool thing is that statistically, if each of these models is unique enough in the way that they are trained, right? Like decision trees and matrix factorization models and regressions and neural networks are very different from each other. And if they are different enough, then your ensemble model can never be worse, right? It will always be at least as good as your best model, but often better, which is super cool because it means if you have computing power, you can't do any worse. So the winning solution for the Netflix rating challenge was won by a team called Belcore, so Pragmatic Chaos. Basically, what ended up happening was there were 3 big teams that were kind of like trying to tackle this problem. One of them was out of AT&T Research and Yahoo. The other one was a consulting company, and then some kind of like amateurs who like built their own team. And they ended up combining their efforts. So the 3 of them were trying to tackle this problem separately. They combined all their efforts, and they built one massive ensemble of all of their models, and they ended up winning. So it's an interesting story because within a few weeks of the contest opening, people made massive improvements, right? Like if you remember, the key was that you had to hit 10% improvement. And people got basically somewhat close to this very early on. Within a few weeks, they got to like 9% or something, or 9.5%. But after those few weeks, it took another 3 years to finally get to the full 10%. They were at like 9 point something for years until they got there. The winning model from Belcore's Pragmatic Chaos was over 500 models, 500 distinct data science models, right? We've learned like a handful. They went clearly above and beyond that and built a significant number of them. And then they combined them in yet another model, right? This is obviously well beyond the scope of this class, but it's super interesting that like to get this 10% improvement, they had to do a significant amount of modeling where each of these models was also like evaluated and tuned and like the complexity parameter was like finally picked, right? And what's really sad is right after they published their winning solution, another team did better than them. Like I think the winning team got to like 10.01% or something, and then another team got to like 10.02%, like right after, which is kind of sad because they didn't win the money. And if you work it out, like how much money they made per hour of work was something on the order of like $1, like $1 per hour across all the people on the team. So a fun effort, but not worth it for the money. Okay. So thank you for listening to all the video. Just going to close with what we're going to talk about a week from today, which is we're going to have a guest lecture from an old coworker of mine who is now an engineering manager of data science at OkCupid. So he's going to talk about the kind of problems that they work on for the first half of class. And then we'll talk about some big data stuff in the data science world and how we deal with big data and how we do machine learning with it. Okay, so again, if you have any questions about anything I covered, please reach out to me. Please do the reading. The stuff I covered is pretty varied tonight, and it kind of sucks that I ended up having to record this. I'll, of course, cover some of this again in class, and we'll do it in the reviews and stuff. But please do the reading, because it also covers a lot of the stuff that I talked about, and will definitely help clear up some things and kind of walk you through examples. If you're having trouble. Okay, again, just shoot me an email if you have any questions.